Welcome to this question on dynamics, where we analyze a mass on a table attached to a hanging mass over a frictionless pulley. A mass on a table is attached to a hanging mass over a frictionless pulley as shown. If the coefficient of friction between the table and the 8 kilogram mass is 0.20, find the acceleration of the masses and the tension in the rope two different ways. We start this question by adding our forces to our diagram. On the 8 kilogram block, we have a force of gravity working downwards. We'll call that Fg8. Equal in magnitude and opposite in direction, we have a force normal upwards, and we'll call that Fn8. As we have a coefficient of friction between the table and the 8 kilogram block, we know that means we have a force of friction acting backwards. We'll call that force fric. Acting downwards on the 6 kilogram block, we have a force of gravity, Fg6, and this force is slightly smaller than the Fg8. We have a force of tension acting equally along all points in the rope. We draw this as a force of tension acting upwards out of the 6 kilogram block, and a force of tension equal in magnitude and opposite in direction acting out of the 8 kilogram block. Although these do not appear to be opposite in direction, as one is pointing up and one is pointing sideways, remember that pulleys just redirect the force. So when we draw this whole system flat, as we're going to in 1 second right down here, you'll see that the tensions are actually equal in magnitude and opposite in direction. So now to simplify the analysis of this system, let's draw it flat down here. All I've essentially done by stretching out the system flat is taken the forces that were redirected by the pulley and just drawing them in the same orientation as the other forces. So now all our horizontal forces are contributing to the acceleration of this system. The Fn8 and the Fg8 come into play when we need to calculate our force of friction. We've made one bold assumption in the setup of our system, and that's that Fg6 is greater than the force of friction. If the force of friction were bigger than Fg6, then this system wouldn't move at all. But we'll proceed with the assumption that Fg6 is bigger. If it isn't in the end, then we can just stop solving our problem and say the system doesn't move. So if Fg6 is bigger, we can assume we're going to have an acceleration in this direction. We can also add it up here so that all our assumptions are laid out. We're accelerating around the pulley and down in the direction of Fg6. We're now ready to start part A and solve for the acceleration of the masses. Since the whole system accelerates, for the acceleration, we're going to consider the whole system. So I'm just going to draw a light box around it to remind us of this. And this is going to become particularly important when we're calculating the tension separately in part B, when we draw a couple more boxes. To find our acceleration, we start with our standard equation for force. Force net is equal to mass times acceleration. We break our force net up into winners and losers. So we're going to have force winner minus force loser is equal to mass times acceleration. And we assume our winning forces act in the direction of the acceleration. So with our acceleration going right, we assume that all forces contributing in the right direction are winning forces, and all forces contributing in the left direction are losing forces. So starting here on the right hand side, we have Fg6, which goes in the same direction as the acceleration, so we call this our winning force. And we'll just start here and work our way left. So we have Fg6, and we keep it positive because we call it a winning force. Here, our first tension works against acceleration, so that's a loser, and we'll call that negative tension. Then here, we have a tension working in the same direction as the acceleration, so that's another winner. We'll call that positive. And then finally here, in the horizontal direction, we have force of friction, which acts against the acceleration, and that's one more loser. So force of fric. And this is all equal to our mass times our acceleration. Now for our mass, And because we're analyzing the entire system, we take the entire mass. So mass total multiplied by the acceleration of the whole system. We start by canceling out our tensions because they're equal in magnitude and opposite in direction, and they conveniently fall out of this equation. Next, we'll expand the different terms of this equation individually so we can track the evolution of the components more carefully. We start with Fg6. Force of gravity, as shown in our list of equations, is equal to mass times gravity. So it's the mass of the 6 kilogram weight multiplied by gravity. Looking at our force of friction term here, force of friction from our list of equations is equal to mu times the force normal. So mu multiplied by the force normal, 8, because the force of friction we're looking at is on the 8 kilogram block. Because Fn8 is equal in magnitude and opposite in direction of Fg8, we can rewrite this equation as mu Fg8. And as already seen, Fg is equal to mg, so we can rewrite this as mu mass of the 8 kilogram weight multiplied by gravity. And for our last term here, the mass total is just the sum of our two masses. So m8 plus m6 multiplied by the acceleration. And now bringing this all back together into one equation, we have m6 multiplied by g minus, don't forget there's a subtraction sign here, mu m8 multiplied by g is equal to our last term here, m8 plus m6 multiplied by the acceleration. Let's bring this to the top so we have room to add in our numbers and solve for the acceleration. Substituting our values, m6 is equal to 6.0 kilograms. Gravity is equal to 9.81 meters per second squared. Subtracting mu, our coefficient of friction, which is given in the question, is 0.2. Multiplied by m8, 8 kilograms. Multiplied by gravity again, 9.81 meters per second squared. And this is equal to m8, so our 8 kilograms, plus our m6, our 6 kilograms, all multiplied by the acceleration. 6 kilograms multiplied by 9.81 gives us 58.86 newtons, and we'll keep extra decimal places all throughout to avoid rounding errors. Subtract 0.2 times 8 times 9.81, which is 15.696 newtons. And this is equal to 8 plus 6, which is 14 kilograms, multiplied by our acceleration. 58.86 minus 15.696 gives 43.164 newtons. And this is equal to our 14 kilograms multiplied by our acceleration. And finally, to get our acceleration all alone, it's being multiplied by 14. So we apply the opposite and divide both sides by 14 kilograms. And this gives us just acceleration on this side, because 14 divided by 14 is equal to 1. And on this side, it gives us 3.083 meters per second squared, keeping a few extra decimal points to avoid rounding errors. And a final answer equal to 3.1 meters per second squared. So this is our final answer for part A. The acceleration of the masses is 3.1 meters per second squared. Because we need this acceleration in part B, let's keep the unrounded value over here. So the acceleration of the system is equal to 3.083 meters per second squared. In part B, we're asked to find the tension in the rope two different ways. And it's always a great idea to find it for the two different individual systems, because it will confirm your answer. If the tension comes out the same for both systems, then you know you found your acceleration correctly. So here we have our green system, and here we have what we'll call our pink system. So the acceleration of the entire system is equal to 3.083 meters per second squared. However, the acceleration of this individual system here due to the force of tension and the force of friction, and of this system here due to Fg6 and the tension, also need to accelerate at 3.083 meters per second squared. So by doing both sides, we can confirm that our acceleration was calculated correctly, because if our tensions are not equal, then we know there was a mistake with our acceleration. We'll start with our left hand or green system here, and we'll solve for tension, starting with our force equation. Force net is equal to the mass multiplied by the acceleration. And as before, we'll do the force of the winner minus the force of the loser. And this is equal to ma. We know that we're accelerating to the right, so the winning force will be our force of tension, which also points right, and our losing force will be our force of friction. So we have tension minus force of fric is equal to the mass times the acceleration. And we'll go through this next part quickly because I just explained it, so it's becoming a little bit redundant. Our force of fric here is equal to our mu Fn, and this is Fn8. And this can be rewritten as mu Fg8, because Fn and F8 are equal in magnitude and opposite in direction, and Fg8, according to our formula sheet here, is equal to mg. So this becomes mu m8 multiplied by gravity. Rewriting our equation with our new term, we end up with the tension minus mu m8 gravity is equal to m8 multiplied by the acceleration. And this is the mass 8 only because we're now looking at this system of just the 8 kilogram mass. Let's rewrite this equation at the top and add our numbers. Substituting our numbers into our equation, we have t minus mu, which is equal to 0.20, it's given in the question, multiplied by our 8 kilograms, multiplied by our value of gravity, and this is equal to our 8 kilograms, multiplied by the acceleration we found in part 1, 3.083 meters per second squared. Completing these multiplications, we have tension minus 0.2 times 8 times 9.81, which is equal to 15.696, keeping some extra decimal points to avoid rounding errors. And this is equal to 8 times 3.083, which is 24.664 newtons. To get our value of tension all alone, we add 15.696 newtons to both sides of the equation. So on this side, negative 15.696 newtons plus 15.696 newtons is 0. So all we're left is tension. And this is equal to 24.664 plus 15.696, which is equal to 40 newtons. And this is our answer to part B. The tension in the rope is 40 newtons. Let's add this down here. Tension is equal to 40 newtons, and solve it using the pink system to confirm our answer. For our pink system, we again start with our standard equation for force. Force net is equal to the mass times the acceleration. And we break this up into the force of the winner, subtract the force of the loser, as we've done twice previously. Similarly to before, because our acceleration is to the right, our winning force is our Fg6, our force to the right, and our losing force is our tension. So our winner is Fg6, and we subtract from this the tension, and this is equal to m6 multiplied by the acceleration, because we're just looking at the system with the 6 kilogram mass. Again, our Fg is equal to our mg, so we have Fg6 is equal to m6 multiplied by gravity minus the tension, and this is equal to m6 multiplied by the acceleration. Substituting our values, m6 is equal to 6.0 kilograms multiplied by gravity, 9.81 meters per second squared. Subtract our tension, and this is equal to 6 kilograms, or m6, multiplied by our acceleration that we found in part A of 3.083 meters per second squared. 6 multiplied by 9.81 is equal to 58.86 newtons, and we keep extra decimal points to avoid rounding errors. Subtract the tension, and this is equal to 6 multiplied by 3.083, which is 18.498 newtons. To get our value for T all alone, we subtract 58.86 newtons from both sides of the equation. On this side, we end up with 0, and on this side, we end up with 18.498 minus 58.86, which is equal to negative 40 newtons. A quick multiplication by -1 on both sides makes our final answer positive. T is equal to 40 newtons, and this confirms our answer from before of 40 newtons. So we've now completed part B. We found the tension in the rope two different ways. First, we found it using the green system with the 8 kilogram mass, and then we confirmed it using the pink system with the 6 kilogram mass. Both yielded the same answer of 40 newtons, which will give us a lot of confidence in our answer to part A of 3.083 meters per second squared for the acceleration, because it's extremely unlikely that you could get the acceleration wrong and the tension still work out the same. Thank you for watching this video on dynamics, where we solve for the acceleration of a mass attached to a hanging mass over a pulley before solving for the tension in the rope connecting the two masses.